All right, so in this chapter we've talked about reversible additions to aldehydes and ketones. We talked about making high rates. We talked about making hemiacetals. We talked about making acetals. We talked about making imines, and we talked about making enamines. Okay, so I want to summarize all these reactions because they have a lot of similarities. What do we know so far? Aldehydes are more reactive towards addition reactions than ketones with very strong nucleophiles. This was in chapter 20. The reaction's irreversible with mild nucleophiles or weaker nucleophiles. The reaction is reversible. In basic media or basically or base catalyzed reaction, or with good nucleophiles. The nucleophile attacks first. So we have our carbonyl. We have our nucleophile. We'll just use a generic nucleophile here. And nucleophile comes in, attacks the carbonyl, and we kick electrons up onto oxygen. So attack in the base catalyzed reaction, we get the nucleophile attacking first or the base attacking first. And in the second step, we have protonation. So common mistake I see in exams in base catalyzed reactions is students protonating the carbonyl first, and you don't want to do that. In an acid catalyzed reaction, the carbonyl is protonated first. So we protonate the carbonyl first in acid catalyzed reaction. Reversible arrows, and we get our protonated carbonyl, which is now more electrophilic. So now weak nucleophiles can attack. So we need to do this when we have weak nucleophiles. And then in the second step, we have attack by weak nucleophile. Such as water or alcohol. Water to make a hydrate and alcohol to make a acetal. All right, so the exception is imine and enamine formation under mild acid catalysis. The nucleophile attacks first. So we saw that that was the last mechanism that we did last time. All right, so that's just a good summary of all of that. Let's talk about other addition reactions of aldehydes and ketones. So we're done with reversible additions, and now we're going to talk about some other additional reactions. And that the one reaction I want to talk about is the Wittig reaction. And I understand you guys are going to be doing Wittig in lab for the next couple weeks. Okay, so I want to talk a little bit about that. So phosphonium ylides add irreversibly, so we're back to irreversible reactions here, to aldehydes and ketones, but they undergo a rearrangement in a second step to introduce a carbon-carbon bond selectively in place of a carbonyl. All right. Let me first show you the reaction and how you predict products, and then we'll go through how to make a Wittig reagent and how a Wittig reagent actually reacts with the carbonyl. So predict the product. First things first, this only works for aldehydes and ketones. Aldehydes or ketones only. So don't try to do this reaction. Don't try to do a Wittig with an ester. Don't try to do a Wittig with a carboxylic acid. Don't try to do a Wittig with an imine, okay, or an acid chloride. So this is only aldehydes and ketones. And here's what the overall reaction looks like, as if we have, imagine yourself slicing this bond in half. Imagine yourself slicing this bond in half. And then you switch partners. The phosphorus always gets the, let me draw this a little more clearly here. The phosphorus always gets oxygen. So we're slicing that in half, we're slicing this in half, and changing partners with the phosphorus getting the oxygen. So that enables you to draw the product really easily. That's certainly not how the mechanism works. We do not cut bonds in half like that and then reattach them. It doesn't work that way, but that's how you can predict product. And then our side product will be triphenylphosphine oxide. So this is an unstabilized Wittig. This is a stabilized Wittig here. And so, but still Wittig reagent. And we're going to do the same thing. So you can get cis and or trans. One of them is going to be major. And I won't say anything more about that because that's one of the things you're going to be looking at in your experiment. And we also get triphenylphosphine oxide. All right, so that's the reaction. This is more of a stabilized Wittig, and this is a stabilized Wittig here, and this is an unstabilized Wittig, and this is a stabilized Wittig. So let's talk about, first of all, how we make both types. So preparation of Wittig reagents, or Phosphonium Ylides is another name for these. So first of all, in order to see how to prepare these, I'm going to draw the resonance structures for a Wittig reagent. It'll kind of help you see how we make this. So we're going to break the pi bond. We're going to move it onto the we're going to move the electrons onto carbon. And so what it would look like is we draw that resonance structure. It looks like that. And that's really where it gets its name from. So Ylide, so this is Ylide, which means that you have a positive charge next to a negative charge. And both atoms with an octet. So that second resonance structure that I just drew is actually, number one, it gives you an idea of how you make this compound, and number two, it also gives you more of an idea of how you actually have, what the mechanism for this reaction is. So to prepare this particular phosphonium Ylide, you take triphenylphosphine plus an alkyl halide. In this case, it would be methyl bromide. SN2 reaction. When you do that SN2 reaction, remember phosphorus is right beneath nitrogen in the periodic table. So when nitrogen species attack do an SN2, you get a positively charged nitrogen, and likewise you'll get a positively charged phosphorus here. In the next step, we need to remove this acidic hydrogen. It's kind of a reach to call it acidic hydrogen. It's not very acidic. pKa, approximately 35. So in order to remove that proton, we need a really strong base. So the base that's typically used for this is a base called N-butyllithium. The N just means normal, so it means a butyl group that is not branched. So it would look like this. 1, 2, 3, 4. That's what it looks like. It's an extremely strong base. Okay, and once you remove that acidic proton with your extremely strong base, you get the Wittig reagent. So positive charge on phosphorus, negative charge on the CH2. All right, so making one of these stabilized Wittigs, you could use weaker bases, and those are the kind that you guys are going to be making in the lab, because you're not allowed to use N-butyl lithium in the undergraduate labs. We're actually not supposed to use N-butyl lithium in that building at all, because it's pyrophoric, and we don't have, that building is so old that it's not sprinklered. So I know you guys aren't using bases of that nature, but those are common bases to use to make Wittigs. All right. Might want to try, just to think about, try making this Wittig reagent by the same method and see if you can understand why we can use a weaker base with that Wittig. Just something to think about as you're doing your lab. All right, so now how do the phosphonium ylides react with aldehydes and ketones? I'm going to show you two ways here. I'm going to show you the way that I learned when I was a student, and I'm going to show you the new way that they're teaching in the book. And it actually turns out that depending on what type of Wittig reagent you use, you could have both of these mechanisms operating at the same time. Okay, so it's a little bit more complicated even than you're doing in the lab. And certainly if we draw the Wittig using the resonance structure where we have the charges, you can see that we have electron-rich carbon, and we have electron-deficient carbon on the carbonyl. And so what's going to happen is that this is going to situate itself so that the positive charge, the negative charge of the carbon here, is going to be nearby the partial positive of the carbonyl, and the negative charge of the oxygen here is going to be near the positively charged phosphorus. So they're going to line themselves up that way. And then the carbon's going to attack the carbonyl. Kick electrons up onto oxygen. Now, if you do this stepwise, I bet you can predict what the next reaction is going to be, right? What do you think? That oxygen is going to attack the phosphorus, right? All right, so we have two species. I'm going to put this in brackets. These are two intermediates. This one is called a betaine. And this one's called an oxyphosphatane. So the betaine, very fleeting intermediate. Oxyphosphatane, intermediate, spontaneously decomposes. All right, so now that's the way that I learned this reaction, and we even have a special name for this betaine. In your textbook now, they don't do this reaction. They kind of combine these two steps into one. So let me show you what they have in Smith. I generally don't ask for this mechanism on exams. I feel like you have enough mechanisms that you need to worry about. So it's going to situate itself just like we did there, where the negative charged carbon is adjacent to the positively charged carbon, and the positively charged phosphorus is adjacent to the negatively charged oxygen, and then it does this all in one step. Like that, to go directly to the oxaphosphatane. And it turns out, depending on what type of Wittig reagent that you have, these two mechanisms actually can be operating. Okay, so it depends on what your Wittig reagent is. And it is in this step right here whether you determine whether you have a Z or an E alkene as your product. Okay, so it's more complicated than you're being presented in the lab. Okay? So that's what happens there. This guy's going to spontaneously decompose, so let's draw the arrows for that. And what you're going to do is we're going to move arrows around in a circle. It doesn't matter whether you go clockwise or counterclockwise. You just want the first arrow going to the phosphorus-oxygen bond to make a new bond between phosphorus and oxygen, and the other arrow is going to go like that, and then you can draw the two products. Oops, I drew that wrong. Let's fix that. Keeping everything right where it is, there's going to be a new double bond here, and then there's going to be a double bond between the phosphorus and the oxygen. So the overall result is a synthesis of alkenes. Synthesis of alkenes from ketones or aldehydes, from a ketone or aldehyde. And if you're grouping your reactions, you may have an index card that has ways to make alkenes. This can be added on to your ways to make alkenes index card if you have one. Or sheet of paper that has that. Okay, so that's the overall product there. Questions? Anybody? All right, so that's how you make a Wittig reagent. That's how the Wittig reagent reacts with the carbonyl. We showed you how to draw the product by slicing and dicing and rearranging. Let's see how we would use the Wittig reaction retrosynthetically. If you're given an alkene and the directions say to make this alkene using a Wittig reaction, you want to be able to take it apart and see what your reagents would be and see whether it's going to work or not. So potentially, and that's a big potentially, any alkene can be made by Wittig. They're not all going to work, but it's certainly a way that we can consider. And the one thing that's nice about a Wittig is it's a really good way to make these compounds like this where the double bond is jutting off of the ring. Those are called exocyclic double bonds, and they're difficult to make by typical elimination. Okay, so those guys are difficult to make. Wittig is a great way to make an exocyclic double bond like that. All right. So let's provide a synthesis of the following amine. Goodness, that should be alkene, right? Using a Wittig reaction, choosing the route that would provide the best yield. All right, so what we're going to do is we're going to take this apart retrosynthetically. Now, when we do a Wittig, one side's the Wittig reagent and one side's the carbonyl. And we're going to take this apart two ways and see which way is the best. Okay, so we're going to form this bond here. And so, and if we do it, we could do it two different ways. We can form that bond two different ways. We can have the left-hand side be the carbonyl and the right-hand side be the Wittig reagent. Or we could have, and we'll call this strategy B, we could have the right-hand side be the carbonyl and the left-hand side be the Wittig. If we did that, it would look like this. So it'd be this plus that. And then I showed you how to make a Wittig, so we could take this apart further. If we were going to make this Wittig reagent, we would need the corresponding alkyl halide. And this would be the alkyl halide that we would use. We'd have that, and we'd have triphenylphosphine. If we were going to go use this strategy, strategy A, we would make this Wittig reagent from this alkyl halide and triphenylphosphine. And what we want to do is we want to choose the strategy that's going to give us the best yield. What do you think? Which strategy would give you the best yield, A or B? A because? Yeah, this is a primary alkyl halide. That is an SN2 reaction. If we use the secondary, that's pretty hindered, right? Secondary, and this should be a hydrogen right here, so go ahead and throw a hydrogen on. I'm going to do that in just a second. The secondary alkyl halide and triphenylphosphine, you're going to get a lot more elimination. So the best strategy is going to be strategy A. So let's fix that. There should be a hydrogen. Okay, so this one's the best. There's going to be less E2 because we have a primary alkyl halide. Remember, the first step in making the Wittig is an SN2 reaction. So primary alkyl halide is going to give you a lot less elimination. That's going to be a better strategy. So then we want to write out the synthesis in the forward direction. We start off with our alkyl halide. Step 1, triphenylphosphine. Step 2, N-butyl lithium. And then we add our carbonyl. And there's our product. Okay. Questions on that synthesis, anybody? So attempting to synthesize this compound using an elimination reaction is problematic. So if we started, these are our two possibilities here for our alkyl halides that we could use. We could start with this alkyl halide, and if we eliminate this direction here, we can eliminate that direction. And what ends up what ends up happening is that you can get some of the correct product, but you will also get some byproduct. Has to be separated. So remember when you did your elimination reaction in lab, what did you get? How many products did you get? Remember you did dehydration, and remember you made the gas and you collected the gas and you did a, remember that? You got 3 products you had to isolate, right? Separate. You didn't have to separate them, fortunately, because those would be very difficult to separate. Okay, so if you started with this one here, your major product would be where the double bond is part of the ring. It's more stable to have the alkene in the ring. All right, so the Wittig is a nice way to do that much more cleanly. All right, and in the last part of this chapter, we're going to kind of revisit 1,2 and 1,4 addition of alpha beta unsaturated carbonyls. And since we're in the aldehyde and ketones chapter, we're just going to talk about the aldehydes and ketones and how those work. All right, so What did we say? We said if we use reagents that do irreversible addition, we're going to get the 1,2 product as our major product. And that's because 1,2 attack is faster. And since all of the nucleophiles, except for cuprates do their own thing, all the nucleophiles attack in the 1,2 position faster. If it's an irreversible reagent, it can't come back off again, and that's why you're going to isolate the 1,2 product. But if you have things that can do reversible addition, like the reagents we've done in this chapter, then they will still more quickly attack 1,2, but they can also come back off again. And eventually, when they attack 1,4, you form the 1,4 product, and it's the thermodynamically most stable, and that's what you end up isolating as your major product. So here's an example here. And so this is a reagent that does reversible carbonyl addition. So it will attack the carbonyl carbon faster, but some of the time it will attack 1,4, and once it attacks 1,4, that's the product that you isolate, because it's the thermodynamically most stable product. Okay, so that's an enolate ion, isn't it? We're going to learn more about those in chapter 23. But for now, we're going to form the carbonyl product. Okay, so we have our amine here. We're going to deprotonate. I do need a positive charge on this nitrogen, so go ahead and throw a positive charge on that nitrogen. Notice all these reversible arrows here. And then now we need to convert the enolate ion to a ketone, to an aldehyde. So using the protonated amine that we just made in the last step, electrons on oxygen are going to come down, and we're going to grab our proton. I'm going to show you the arrow pushing 2 different ways for this step, because some students don't like it this way. I'll show you another way that you can use. So now we have our carbonyl. So it looks like that, and then we have ethylamine as our side product. If you don't like it that way, there's another way you can draw this arrow pushing that might make more sense to you. And what it would look like is this. I'm going to redraw that compound. And the other way to do this is to draw the resonance structure for the enolate ion. So to draw the resonance structure for the enolate ion, we push electrons down here, put electrons on carbon there. So this is a resonance structure, so I'm going to do resonance arrows and brackets. And there you can see the negative charge on carbon right there. And so then we can protonate with that. We can protonate from that resonance structure. So these are just 2 resonance structures of the same compound. So you can really work from either resonance structure. It does not matter to me. And that will give you the same compound. Questions on that mechanism? Anybody? How we did that? All right, let's see a vote here. Who likes the first way I did it in red? Okay, who likes the second way? Okay, just a few of you. All right. Okay, so recall 1,2 addition is faster, has a lower energy of activation. So when reactants that do irreversible addition react, they attack the carbonyl and then are stuck. Weaker nucleophiles reversibly add so they can come back off again, and some of the time the molecules are going to have enough energy to overcome the higher energy barrier and do 1,4 addition. So you can see right here, this is 1,2. There's the energy of activation for the 1,2 addition. It is smaller, so it's a faster reaction. EA for 1,2 addition. Some of the time when those molecules collide, they're going to be energetic enough and properly oriented to do 1,4 addition. So here's the energy of activation for 1,4 addition. So higher energy to do 1,4 addition, higher energy of activation. Okay, so once you go down here, now this lower energy transition state brings you to the 1,2 product, and here's the energy diagram as we move to product here. This other, the 1,4 addition on the other hand, so this would be lower energy of activation, boom, it goes here. That's actually a higher energy intermediate than the enolate ion down here. And that continues, and then this also goes to the higher energy product. So some of the time, the molecules have enough energy to go and overcome this larger energy barrier. That goes down here, all the way here, and then goes to the more stable product. Now, which one of these reactions is more likely to reverse? From here or from here? This one, right? Because for this to reverse, it has to come up with how much energy? It has to come up with a lot of energy to go. It has to go back here, and it has to go all the way back here. Okay, so once this goes here, it's much less likely to reverse because it takes so much energy of activation to reverse. So the term we use for that is a thermodynamic well. It's like it's fallen into a well and it can't get back out again. And eventually the molecules are all going to fall into the well, and that's what you're going to isolate. Okay? So it's too stable. It's not going to go back again because it has to come up with way more energy than this guy to go back again. So that's the idea here. All right, so less stable product here. Let me scroll up a little bit here. Less stable product. More stable product. So over here on the right-hand side, why is the energy of activation for the 1,2 product smaller? Why is that smaller? If we look at the hybrid for an alpha-beta unsaturated carbonyl, let's look at the hybrid here. I'm going to leave all the extra groups off and just focus on the backbone here. So it's going to look like this. And how can you get the hybrid? By drawing the resonance structures here. You can come up with the hybrid. So we have we're going to have partial negative charge on oxygen. We're going to have partial positive here, and we're going to have partial positive here. And so the reason that the energy of activation for the 1,2 product is smaller is that there's more partial positive charge on the carbonyl. There's more partial positive charge right here. More partial positive charge on carbonyl. So it's more electrophilic. It's more electrophilic than the carbon on the end is. So it's going to be easier for nucleophiles to attack the carbonyl carbon rather than the at the 1,4 position, which would be the beta carbon. All right, questions? Anybody? All right, so we have one more problem to do. I don't know why do I say example 4 here? I think we need to take that 4 off of there, right? Oh, I did. It's on my notes here, but it's not in here. Synthesis example. Okay. So devise a synthesis of the following 2 compounds from the given starting material. And you can see it's not very obvious here. You just have to remember when you have an alpha-beta unsaturated carbonyl that we can form the 1,2 and the 1,4 product. So when it turns out that one of these So if it's this, we have a carbonyl, this is the alpha position, this is the beta position. In the 1,4 product, we have a nucleophile incorporated into the beta position. So you want to pick out the nucleophile here. Over here, our nucleophiles is actually on the carbonyl. So this is the 1,2 product, 1,2 addition. This is 1,4 addition. So if we want to do 1,4 addition, we have to use either cuprates or things that do reversible carbonyl addition. If we want to do 1,2 addition, we have to use really powerful nucleophiles. So for the 1,2 addition, what would be our nucleophile? Yeah, Grignard organolithium, right? Use powerful nucleophile. All right, so there's our starting material here. Step 1, we'll use Grignard. I'm feeling in a Grignard mood today here. Ethyl magnesium bromide followed by water. That gives us an alcohol. And what do we still need? What do we need to do to get the product? H2 palladium, how about that? So that's the 1,2 product followed by a reduction. The other one is the 1,4 addition. So for the 1,4 addition, we use a weaker nucleophile or a cuprate. Step 1 cyanide. Step 2 H3O plus. By the way, since I haven't put up the podcast for nomenclature, we're not going to have nomenclature on this exam. We're going to procrastinate and have it on exam number 2, midterm 2, okay? So no nomenclature on this exam. Questions on chapter 21? Anybody? Yes? That's on the podcast for nomenclature. So when you have a carbonyl, the carbon that's adjacent to the carbonyl is alpha, and then you count using the Greek letters as you go out, alpha, beta, gamma, delta. Okay? Yeah. More questions? So let's save this, and then we'll go back to, we're going to start on chapter 22. So in chapter 22, we're going to do the same thing we did in chapter 21, but now we're talking about type 2 carbonyls. Any questions about the exam while we're waiting for this to save? All right. So carboxylic acid and their derivatives. We call them type 2 carbonyls. All right, so let's review what we know about type 2 carbonyls. They have a group L that has lone pairs. And so this is our generic. So we draw it like that with lone pairs. That's our generic structure. We have acid chlorides, we have amides, esters, carboxylic acids, and anhydrides. Let's look at some physical properties. Boiling point here, 118 for a carboxylic acid. 52 for a corresponding alkyl halide, acid halide, acid chloride. 77 for an ester. 221. That's not a mistake. 221, 139, and 270. All right, and let's look at solubility, and then we'll talk about some of these trends here. Infinitely soluble for acetic acid. Acid chloride reacts violently with water. So we can't really measure its water solubility, right? Reacts violently with water. We'll talk about the product that you get when that reacts violently with water. An ester with an ethyl group, 8.6 grams in 100 mils of water, in 100 grams of water. Amide, 97.5 grams in 100 grams of water. Anhydride reacts with water, so we can't really measure its solubility. And carboxylic acid, long-chain carboxylic acid, notice the 8 there. We have 0.015 grams in 100 grams of water. All right, so as we're increasing the chain, carbon chain here, we go from methyl, and now we go to 9 carbons here. From 1 carbon here to 9, greatly decreasing solubility, but increasing boiling point because we're getting higher molecular weight, right? Let's see, what else? Why would an carboxylic acid be higher than an acid chloride boiling point? This can hydrogen bond with itself, right? Remember they form dimers, okay? Ester, can that hydrogen bond with itself? No, so even though it has a higher molecular weight than the carboxylic acid, it can't hydrogen bond with itself, so it's going to have a lower boiling point. Why does this one have such an enormous boiling point here? Why is that so much higher? Does an amide form as strong as hydrogen bonds as a carboxylic acid? No. So why is this so high? It has an extremely large dipole moment, that molecule. Okay? We're going to talk about that coming up. It has a very large dipole moment. That's why it's so high. Very unusual dipole moment here. And we'll talk about why in just a second. Has very large dipole moment. We mentioned it in chapter 20, but let's look at that again. All right, so both carboxylic acids and primary and secondary amides can form hydrogen bonds and therefore have higher boiling points and greater solubility than other type 2. And so here's our dipole-dipole attraction. Let's draw the resonance structure here that gives us such a large dipole. So I'm going to move over to the left here and draw the resonance structure. So this is formamide, and then we have formic acid. And then let's compare that. We'll put brackets around that. Let's compare that with the carboxylic acid. And we'll write down the dipole moment here. .73 debye. That's huge. For formic acid, it is 1.4 debye. Okay, so the reason is that this second resonance structure plays a really large part of the hybrid for two reasons. Number one, nitrogen, when going from this resonance structure to this one, nitrogen is donating its electrons. And what do we know about the base strength? Remember, we related base strength to resonance stabilization. Is a nitrogen or oxygen a stronger base? Nitrogen by far, right? So that means that since nitrogen is such a strong base, it really wants to kick in its electrons much more than oxygen. So it kicking in its electrons, it moves electrons up onto oxygen, so we get a negative charge on oxygen. We get a positive charge on nitrogen. This can do the same thing, but it's not as basic. So it's not as likely to donate its electrons. We still are forming this negative charge on oxygen, but the positive charge is not as happy on oxygen as it is on nitrogen, right? So all those reasons combined. So we got to remember, and didn't we draw this resonance structure in chapter 20 when we were doing the lithium aluminum hydride plus an amide? And we said that this is really important here. That resonance structure is really important. Okay, so very similar to that. Tertiary amides have significantly lower boiling points despite the fact that they have higher molecular weights because they cannot form hydrogen bonds. So if we compare the two of these, this is 221 again. This is 166. So we really have two things making this boiling point so high. For an amide, we have this enormous dipole, and we have hydrogen bonding. And when you can't have the hydrogen bonding, it's going to lower it. But that's still pretty high, isn't it, for no hydrogen bonding? Okay? Questions? Anybody? Some famous class 1, why do I say class? Let me see if I fix that. I did fix that. Some famous type 2 carbonyl compounds. Cocaine. What functional group do we have in that one? Esters, right? Novocaine, esters, LSD, amide, Valium, amide, right? These are all type 2 carbonyls. Caffeine. Something that looks like an amide, it's not quite an amide, it's like a double amide. Phenobarbital, same thing. We have an amide, but it's like an anhydride with a nitrogen, right? Okay? Prostaglandin A, carboxylic acid, citric acid, carboxylic acids, esters. These guys, smells like peach. So these are used in the perfume and artificial flavoring industry. And this is banana oil. Some of my students made these this week. All right, so flavors and scents. Okay, we'll stop. Oh, no, we have one more minute. Sorry. Ah, come on, man. Nomenclature. C, podcast. Okay, let's scroll. Let's see if we can throw in one more thing here. No, we can't. We'll stop right there. I hope you guys have a great weekend.